After a successful decade run as a feature documentary, Eyes of the Mothman is now a podcast containing bonus information and, for the first time ever, the complete, unedited field interview tapes with eyewitnesses, experts, and those who were directly impacted by the Mothman incidents that occurred in Point Pleasant, West Virginia in 1966 and 1967. Although this podcast is meant to act as a historical record and an archive of the events that transpired, all material contained here is not for reproduction without the written consent by the copyright holder, Redline Studios, Incorporated. Episode 23 of Eyes of the Mothman, the podcast, is a look back at our raw field interview tape with James Beichler, who is an associate professor of physics from the West Virginia University at Parkersburg. Do you guys remember James's interview? This was one that happened very last minute. He was a friend of Susan Shepard's, and I kind of remember it being like, hey, my friend's a physics professor. Do you want to talk to him? And honestly, at that time, with my age, and there's a reason I went to film school. It's because I'm dumb. But it's like, hey, do you want to interview this professor of physics about Mothman? And I just was not prepared at all for this, to where I just look back at my line of questioning and it's like, how does the world work?
Yeah.
And I kind of admittedly was not prepared to interview him and to try to find a way to really fit his expertise into our story. But I kind of remember what I pulled out of it was the idea of, was Mothman, or could there be this thing of like interdimensional beings or like multiple dimensions? Because people would describe Mothman as like appearing, disappearing, kind of like, yes, it flew away, but it was very much like here it was, there it wasn't. And so I do remember us kind of talking with James a little bit just about the idea of the existence of other realms and dimensions, and like, is that science fiction or fantastical, or is it somewhat grounded in plausibility and possibility? And so I do remember his interview being way above my head, but I know it was geared towards the idea that there could be other planes of existence beyond 3 dimensions of space and being like a 4th dimension.
I did not understand anything that he was talking about. That's all I remember.
Well, I mean, it sounds like you saw an opportunity to get another scientist, and you didn't want to pass that up.
Correct.
If it would add validity and legitimacy to your story and to the story that you're telling. So I think that you're like, all right, might as well light this guy and see what he has to say. We can use a few sound bites here and there. It's weird where you have to go, are there other dimensions? It's just like, just give me whatever you have and I'll chop it up and make it sound the way I want it to sound.
Yeah, it was someone who was like available, and it was an opportunity that I didn't want to say no to, but I just, again, was not really prepared for it or sought after it, like someone like that, which is a very specific field of expertise. Obviously in a normal situation, you would take days to research and kind of go, all right, how can I steer my questions to this person to really lend itself to our film? I'm glad that he still had a contribution to the film and was still there, and it was an interesting take. And I remember that, again, our connection to him was through Susan, and I believe, part of his work or hobby was being involved in the paranormal, being involved in like ghost hunting and things like that. So I know he was coming from a perspective of science, but also a love of the paranormal. And so I could be mistaken, but I do remember us kind of trying to gear our conversation more towards Mothman as being something supernatural and something fantastical. And so that was our purpose for interviewing him. He was a very nice guy. Again, when you're doing stuff like this, am I going to sit down for him with 2 hours? No, but like anytime someone wants to contribute something to your film, you can always film it and leave it on the cutting room floor. And so, he ended up making the final cut. So he did have some interesting things to say. I am curious to revisit our conversation. I probably sound like an idiot because I was not ready for it, but I think he did a great job. And so I'm curious to revisit that interview in its raw state. Here is James Beichler, professor of physics from West Virginia University at Parkersburg, Hopefully you enjoy this field tape interview.
I imagine there's no teeming masses of people here to bother you.
No, that's a good thing too. No one, and filming anywhere and anything is like no problem. Just do it, you know. Like whereas anywhere else, it's like paperwork on paperwork.
Yeah, we don't have a big government here, like in a big city to deal with.
Yeah, so that's been a nice difference.
Okay, camera speed.
Okay, good. Just don't forget to get the other shot too. So I'll go through a couple things with you, just which always make the interview sound nice, kind of like guidelines to work with. So if you just talk to me and not the camera, that always looks nicer. And just try to, as if the camera's not here, type of thing. I might ask you a question more than once. That just means I might ask you the same question more than once. I might just try to get a couple options to choose from later on. So it might be redundant. Sometimes I might ask you the same.
That's okay.
The best thing, the one rule that's good to follow is to know that later on when I use your segments, my question is not going to be there. So if you can reiterate the question and your answer, it always sounds good. Like if I ask you, how's the weather today? If you say good, later on, all I'll have is good. But if you say, it's raining outside today, it's kind of like a complete thought. People know what you're talking about and all that. So if you try to use that, that usually works well. And if I ask you something that doesn't make sense or it's like wrong or incorrect or doesn't fit to your area of expertise, just tell me. I might have something wrong. All right. So first, just so I have it later when I edit on the tape, can you just tell me your name once more and then spell it for me also?
Okay. James Beichler, B as in boy, Eichler.
And what would your title be?
I'm an associate professor of physics at West Virginia University at Parkersburg.
Great. So the first question I wanted to ask you about is a little bit about the electromagnetic spectrum. What it is, just how it's broken down, and then if you could talk about where UV rays and visible light border one another, and then a little bit about UV rays.
I should just state my lecture in class last week before finals. Okay, the electromagnetic wave spectrum is the light wave spectrum. We see light as waves or particles. That's called the wave-particle duality. If it's a particulate in nature, we call it a photon. So some people talk about photons rather than light waves, but they mean the same thing. In modern physics, whether it's a wave or a particle photon depends on the experiment you do to detect it. Like light coming out of a laser is particulate because that's the way it's created. But we can run tests on it, a diffraction pattern, do a diffraction grading and show the wave characteristics. As an electromagnetic wave, the theories were developed in the 1860s by James Clerk Maxwell. At that time, we had the visible light spectrum, infrared, and ultraviolet. The spectrum runs from red, orange, yellow, green, blue to violet. And that's from 400 nanometers to 700 nanometers. A nanometer is a billionth of a meter. So they're pretty short. That's the visible wave spectrum. Because the speed of light is constant, speed of light is equal to the wavelength times the frequency of light. A longer wave means a higher frequency, a longer wave means a lower frequency, which means the frequency is proportional energy. So lower frequency means less energy. So the red end of the spectrum is the low energy, longer wavelength. The violet end of the visible spectrum is shorter wavelength, but higher frequency and higher energy. Then above the violet, you have the ultraviolet. That's outside the human range of seeing. The ultraviolet range runs, it's 4 or 5 times wider than the visible range. The visible range that we see red through violet is actually very small. It's only an extremely small portion of the whole electromagnetic spectrum and right dead in the center. So I guess that's an evolutionary thing. Ultraviolet is higher energy. You have the shorter and longer ultraviolet. The shorter would be the higher energy. And when you get to the shorter, you're approaching the X-ray range. Then you have the X-rays, and then even higher energy than the X-rays, you have gamma rays, all the way out to cosmic rays. Higher energy, how much energy in their frequency and wavelength depends on how they're created. The visible light waves are created in the outer shells of the electron, the outer electronic shells of the electron. The ultraviolets on the inner shells, and X-rays are created in the innermost shells of atoms, with the big atoms, like metallic atoms. And so that's why they're higher frequency, because they're bound tighter to the nucleus, so which means they're higher energy to liberate the electrons. And when an electron falls back in the shell, the electromagnetic wave is created. Then finally, the gammas are created in the nucleus of the atom, which is the smallest part of the atom, so it's the highest energy, shortest wavelength. At the other end of the spectrum, we have longer waves than the red, would be the infrared, so they're lower energy. And beyond the infrared, you have microwaves. By the time you get to microwaves, the size of the wave is about the size of a water molecule. That's why you have microwave engine or microwave oven, which makes your water molecules vibrate to heat your food. And then you have short waves, medium waves, and long waves, which are the radio and television bands. And how long can waves get? By the time you get out to the very long waves, you're in 100,000 meters length. But they're very, very low energy. At either end, the shortest waves would be the gammas, cosmic rays. And then the longest ones would be the long waves. They're used for like ship-to-shore communication. And there's no extent. They could go as long as you want or as short as you want. The only trouble is if they go too short, we don't have anything to detect them because they're smaller than any measuring instrument we have, which would be a proton. And at the other end, they could go as long as you want. You could literally have a wave that's the length of our solar system, theoretically, but it would be of such small energy, there would be no way to detect it.
You don't have to go into detail of what separates
just from one end to the other.
Just tell me one end to the other what they are, and then in the order that we would find them on the spectrum.
Okay, the order would be cosmic rays, gamma rays. They're the high energy, short, very short. Again, about the size of a proton. Then you come into your X-rays. Then you come into your ultraviolet. Then you have your visible spectrum, which going from the high energy end, it'd be violet, blue, green, yellow, orange, and then red. Red is what we call the hottest because it's absorbed easily by particles, so it's heat rays. So red, then infrared, you're going less energy, longer waves. Then after the infrared, which is not visible, non-visible, you have the short waves, medium waves, and long waves.
And can you talk a little bit about the ultraviolet spectrum? Can you just tell me what it is and just give me some examples where ultraviolet light or rays would be found and exist and what the effects they would have on people? Like ultraviolet rays are the same things like emitted from the sun, right? They all can give sunburns and things like that. Can you talk a little bit about that?
Ultraviolet are outside the visible spectrum. They're higher energy, but much shorter than our wavelength. So they're out in the range of 400 nanometers or less, down to in the single nanometer range. Again, a nanometer is a billionth of a meter. They're higher energy. Energy is related to penetrating power. The opposite of penetrating power is absorption. So ultraviolet being higher energy, see the visible light rays reflect from objects, and then that's how we see objects. Ultraviolets are higher energy, so they penetrate. Now, the ultraviolet has enough energy that it penetrates 2 or 3 layers of skin. Then, of course, after it penetrates, it's absorbed. Now, if it's absorbed, when it's absorbed by the skin, if it's absorbed by, say, a DNA in a cell nucleus, and then that could cause a mutation, which could become cancerous. So ultraviolet are more higher energy outside the visible spectrum, and they have more penetrating power, but only, as I said, enough penetrating power to go through a few layers of skin. And they're very common. They're everywhere. They're as plentiful as normal visible light rays.
And can you give me some examples of where ultraviolet light is either emitted from or originates from?
Well, commonly it's emitted from the electronic shells, the inner electronic shells of atoms. So they're produced everywhere. And of course, that's where it comes from in sunlight. You have energetic atoms, electrons being knocked out of lower shells and higher shells, falling back into lower shells, giving off the ultraviolet rays. So it's essentially the same place everywhere. They come from the electronic shells of the atoms. Those atoms can be anywhere.
Is it possible for other things to exist within these spectrums that we cannot see, that are there, but we cannot see them?
You mean within the visible spectrum?
Not within the visible. Like, is it possible that there are things that exist in the ultraviolet spectrum
sure.
that are there but not visible to the human eye?
Well, see, we don't see things because things emit light. We see things because they reflect light. So theoretically, if you have something that absorbs all frequencies of visible light and reflects ultraviolet, then we wouldn't see it. For example, stealth technology for the military. They have the angles and everything on the airplanes so that they scatter the waves, so you don't have the waves bounce off and come back to a radar source. They scatter the waves in all directions and absorb the rest of the waves. So that's why you can't see on radar, why you can't see a stealth plane. So it'd be that type of technology, yes.
And I had read an article, just in another example too, that they were talking about things that could exist in other spectrums. And one I think was I think it was in the ultraviolet spectrum or maybe even beyond it. But I had read this article about scientists using telescopes that were seeing an ultraviolet in the ultraviolet spectrum to look in outer space, and they were actually seeing some things out there that were not visible by, visible light. They were actually finding some planets that were actually, or stars or some things like that were existing, but only under that spectrum. So can you talk a little bit about that? The idea that there's something solid existing there, but beyond what we can see with the naked eye.
Yeah. Of course, stars emit all types of electromagnetic waves. Some of the smaller stars, or I shouldn't say smaller, I should say some of the bigger stars, red giant, emits in a red frequency, so it's less energy. It's a thing about energy. Red is less energy than violet, so if you have a big star like Betelgeuse, which is a red giant, it emits it in the red spectrum. Red is more easily absorbed by dust because the red wavelength is about the same size as dust particles. So interplanetary dust will absorb red. But maybe the infrared will come through. So we use special films and such and detectors to pick up the infrared. And so we may see other stars in the infrared spectrum because the other colors are absorbed or because they're not emitting in those spectrums. They're very low energy stars. And there's a group of stars that are theoretical called brown dwarfs, that they have so little energy and they're so small, 5, 6, 7, 8, 9 times larger than Jupiter, that they have very, very low energy fusion engines running them. So they're very low energy. So we don't see them at all. As we have special films and detectors, we may see these in the infrared and the lower energy spectrums.
Is it correct to say that there are things that are of matter, of substance, that can kind of exist in different realms outside of the visible light?
Yeah. It'd be a little bit more problematical on Earth because we obviously, our visible light range is such that we evolved that light range. So it would have evolved so that we could interact with everything in our immediate environment, which would be the Earth. There could be fish or other animals that see different spectrums than us. We basically all have the same spectrum, but maybe deep water fish might see into the infrared or into the ultraviolet. But I think it'd be less probable, say, not impossible, but less probable that there would be natural things on Earth that we wouldn't see through evolution theory.
It's more plausible that it would happen by manipulating the spectrum as opposed to just naturally existing there.
Yeah, manipulating the spectrum. Of course, the military is working with that, not just in stealth. The Arnold Schwarzenegger movie, what was that? Not Terminator. The other one he did where he is in the jungle fighting an alien being.
Predator.
Predator, right. The Predator.
Start with that. Can you start it with, the film Predator is a good example.
Yeah.
And then, maybe that people, when they see that film, they think it's all science fiction, but is it actually?
No. From what I heard on a TV special, an American general saw the movie Predator and said, I want that. And so the military is actually working on that, some way of bending the light rays around an object so basically you can't see it. It's personal stealth technology. You can manipulate the light rays so that you can't see something. Again, we see objects not because objects emit light. Stars emit light. Other things don't. We don't have fusion engines where we emit light. We do emit some electromagnetic waves. They're called biophotons, but they're nothing in the visible range. They're very weak energy. And I know the experiments done by scientists trying to capture biophotons are done in total absolute darkness. So any light rays that we would emit would not be visible under any normal circumstances. Since we see things by their reflected light, all we have to do is, as I said before, is stop reflecting the light and something would become invisible. But then, like if I were wearing some type of garb right now that absorbed and didn't reflect light, you'd see a black hole. You'd see a nothing because I'd be absorbing the light, not emitting it. What you want, that wouldn't be good. What you want for stealth technology would be something that stops emitting light or stops reflecting light, but something that will bend light rays from behind me so you see what's behind me. Literally bend light waves around me so that you see what's behind me. So it's a little bit more complicated than just stopping something from not emitting, but stopping something from reflecting light.
You can leave that on your lap if you want
Okay.
to, so it's not a problem. You can talk with your hands if you want. So I want to focus on that a little bit because I think it's interesting. And I think we could throw it on another chair too if you want. Is it
If this is long enough, I can set it on there. No, it's sliding off my pants. That's why it's holding it. I think that'll work.
So I think that the Predator is kind of a good example because kind of, everyone knows that film and everyone sees it as science fiction, not really science fact.
I think bending light around an object so you could stop an object from reflecting and absorb light instead of reflect it so it becomes invisible. But then again, you have to see the light bent from behind so you can see something behind the object. Bending light around an object is not feasible because you'd be talking about manipulations to light waves that we can't do. Scientifically, very, very improbable. I think probably what you could do, though, is with very high-speed, lightweight computers now, absorb light on one side and emit it from the other side, like you'd be a three-dimensional TV screen, literally. So the picture that's in back of me, the computer would pick it up and then re-emit it here so that you'd see what's in back of me. That's more feasible. And I think that's probably what the military is trying to do. I'd really like to know if they finish that project. It'd be sort of neat.
It's funny, just as a side note, I actually saw that too. They pretty much did. They have this suit now where it's millions of cameras that films this way.
Yeah.
Oh wait, is it? No, it films. Sorry, it's on the back. It's got these millions of cameras that film what's behind you, project it in like a size of a pixel on your chest.
Yeah.
And it's literally like you're invisible. And I saw an example of. I don't think it's been perfected, but I saw an example of at least of just the chest, and it's like literally person vanishes. It's crazy.
Yeah. Well, I mean, even 007 did that, one of the later movies a few years ago. He had the car that had the same technology, so his car, in essence, turns invisible.
What I'm trying to do is a lot of times people will see something during the day or just during normal situations where it's like something's there and then it's gone. With different things. Sometimes people just, whether it's something solid, some whatever. There has been cases where people will kind of see something and it appears to just like vanish into the air. And one thing I'm trying to suggest is possibly, are they witnessing something that's kind of bleeding in the spectrum for a few seconds and then back to the other? Is that possible that something, does that make sense that if visible light borders UV light, that's something that's of more of a UV reflection or emitance that exists there? Is it possible that it can kind of bleed into visible light momentarily in the back? Is that possible?
Ooh, tough question. Let me see. Is it possible for something to more or less enter our spectrum, something is outside of our normal spectrum in the UV range, enter our spectrum and leave it. There are ways to change what we see. Light waves bend when they go through water. Light waves bend when they come through glass. They bend by slowing down. So it's possible that possibly through some curvature of glass, or if it's raining or very misty or something might bleed in that we wouldn't normally see because the light waves are scattered and funny things happen to them.
No, actually, it's funny that one thing that's consistent with people that see things like that, a lot of times it happens during like lightning storms and things like that. Would that make sense? Would that be a scenario? Or
yeah, changes in atmosphere could. Atmospheric changes, amount of moisture in the air and such could possibly change the spectrum a small amount. Not very much, though, I don't think. One that you're not bringing up that might be important would be how our brain works. You talk about things appearing and not appearing, and I think that's more of a matter of brain function. Now, the brain function is out of my field, but I do work a little bit with it. Like when we look at a movie picture, we see 30 frames per second. If we have 20 frames per second, it's real jerky. Well, our mind works, as far as we know, our brain works in a similar manner, that there may be things that are moving not in a different spectrum, but at different speeds relative to what our brain can absorb, so we don't see them. So there are some other optical phenomena rather than light emission, absorption, or reflection that could render something invisible to us. If it's vibrating extremely rapidly, we might not see the vibration. Right. The vibrations are actually faster than our brain can detect. That it might appear a blur to us. It would just become a blur, and then it might be invisible if something was vibrating fast enough. Say if you just take a tuning fork, a long tuning fork, it's a solid object, but you can get it vibrating enough so that it appears blurred. The faster something vibrates, the more blurred it would become. So perhaps something could vibrate fast enough that our brain couldn't detect it. And that's not a physics problem, that's a physiological problem. Talk to an optician or an optical scientist, because that depends on how the brain works. A solid object is determined as solid because of the electrical forces, basically static electricity, static electrical forces that hold the molecules together. Now, when you see a solid object, if you talk about solid as being material, matter, having mass, weight, solid objects aren't solid because most of the weight or the mass of the object is concentrated in the nucleus. So 99.99% of an object is not materially solid. If that's true, we're not materially solid, so we should be able to stick our hands, right through our other hand. But we can't, not because of their being solid, because the electrostatic forces, they're binding the molecules together. So when I put my two hands together, it's basically the electrostatic forces that allows me not to put one through the other. Now, if you take something like smoke, as you said, the smoke molecules are just ash molecules in air. They're not held together. You have very small molecules, or ash particles rather. You have small ash particles, and they don't have the static electric forces, so they're not bound together. So when you put your hand through, they move around in fluid motion. You think of fluids as being liquids. No, fluids are gases and liquids. And something that is fluid would follow laws of fluid dynamics, so that if you put your hand through, they form around. If an object, say an object in this room right now, were emitting and or reflecting ultraviolet light, we would not see it. But as I said, unless it's manipulating the light rays around it artificially, we'd see a black smudge or something like that, because we couldn't see what's behind it, because it's reflecting the light, absorbing and reflecting the lights behind it in the opposite direction, away from us. So you'd have to assume that if you can't see something, it's artificially manipulating the wavelengths or the frequencies of light. If it's artificially manipulating them, sure, it could just pop in and out. of our visible spectrum just by manipulation, if it wanted to be seen.
And, one side effect of being exposed to ultraviolet light is, like we talked about, a sunburn. Could the effects of what comes with the ultraviolet rays, could that affect you? Like, if something slipped in, could I get a sunburn from it if it just slipped in for 10 minutes? Can you talk about that?
If it's emitting ultraviolets or reflecting only ultraviolets, it'd have to be emitting them, because the ultraviolet rays in a room right now are not enough to do harm to the skin. But like you say, sunburn comes from ultraviolet, because our skin is absorbing all that energy, and that burns the skin. It's almost like an abrasion, with the photons hitting our skin and being abrasive to our skin. So it irritates the skin, turns red. And that's why on a cloudy day, you can get some really nasty sunburns. If there's a high ultraviolet source in this room, if it's intense enough, yes, we could get basically sunburn. Same type of sunburn you get on a cloudy day, the one that really hurts bad, turns your skin red. Can something, if we were exposed to it for, say, 10 minutes, and it's a high intensity of ultraviolet emitter, could we be burned by it? Yes, we could, depending, again, on the intensity. For example, if I'm out in a cloudy day for a half an hour, a summer day, I'm going to get burned because I have lighter skin. Different people's skin have different sensitivities to it. Person with darker skin, their darker skin is going to be more reflective, so they can't get burned. Although it doesn't matter how dark your skin is, you can still get burned by ultraviolet. An African-American friend of mine who had light black skin, she went up to Yosemite National Park and got her first sunburn in her life, and it really pained her quite a bit because she wasn't used to it. So the skin can react to high-intensity waves, depending on intensity, in as short as 5 or 10 minutes. Very high-intense wave.
This podcast is a companion piece to the original feature-length documentary film from 2011 of the same title. If you're enjoying this podcast, we encourage you to see the film that started it all by visiting www.eyesofthemothman.com.
Something that's kind of manipulating these fields that we're talking about. When they do that, are they therefore changing which spectrum they're now visible in? Like, is it now out of the visible light spectrum? But if we were looking at that same thing with ultraviolet, in the ultraviolet spectrum, would we see it? Is that what?
No, it's not changing the spectrum it's invisible in. It's altering the waves that are already there. Again, it probably would not be an emitter. It would probably be a reflector. So it's just changing its reflectivity. It would be like you could change reflectivity of a mirror by just scratching it, taking sandpaper and scratching the face of the mirror. So it doesn't reflect directly, it disperses the light, and you can't see your image in a mirror anymore. So it's the reflectivity is the important thing.
Would it then put it at risk to someone who's next to it? Like, could they now have effects of ultraviolet rays because it's changing?
No. You couldn't reflect. You couldn't reflect enough ultraviolet rays just from your immediate environment here on Earth. There aren't that many electroviolet waves of high intensity here because they're blocked out by the upper atmosphere. You'd have to, in order to have enough ultraviolet rays, intense enough source, you'd have to have a way of concentrating, either concentrating or focusing the ambient ultraviolet waves that are in, say, this room, or emitting them yourself. So normally, if you're next to something, if it's just absorbing so you can't see it, you wouldn't get the ultraviolet effect.
Is energy kind of the initiator?
Well, everything has energy. There'd be some debate at this point because some modern physicists think energy is the most basic thing in the universe, and that even matter is energy. I'm one of the ones that think otherwise. You have two different types of energy: potential energy and kinetic energy. Kinetic energy is the energy of something moving. So all vibrations and everything, the more the movement, the higher the energy. Potential energy is when you put a material object in a field, a gravitational field, electrical field, or magnetic field. Potential energy is essentially stored energy. So just it's the relative position of material objects within a field. As I said, a magnetic field, electric field, or a gravitational field. So everything would be of that type of energy. The important one is motion. Even heat is motional energy. Heat is due to the vibrational kinetic energy of molecules and atoms. So in that sense, yes, energy is extremely important. Energy doesn't create something. Everything has energy. Everything has energy, either potential energy, the potential to move, or it has motional energy, kinetic energy of some form. So because everything has energy, either potential or kinetic, a lot of scientists use energy to describe the world around us rather than using material particles or matter to describe it. If you're using matter, you're going to talk about the forces. If you're using energy, you're going to use the conservation of energy laws to describe something. So it's not that energy is being created, the energy is already there. And so energy just gives a convenient way for scientists to describe something. How they manipulate that energy would determine their effect on the environment and everything around them. A lot of people with unexplainable phenomena, whether it's ghosts, a Mothman, or anything else, if they don't know physics, they try and use an excuse to explain it. That excuse is energy. Without knowing what energy is, a lot of people who don't know the physics and the chemistry of a situation say it's energy, it's energy, it's energy. And so I always ask, they talk about spiritual energies and all different types of energies. Well, there are no such thing as far as physics is concerned that we have detected. Everything is either potential energy, as I described, or a kinetic energy. A physicist would try, if a physicist believes a phenomenon is real, the physicist will try and explain that phenomenon in terms of the known energies, kinetic energy and the known potential energies. He will not declare a new energy, a spiritual energy, a ghost energy, whatever kind of energy. That's the mark of someone who doesn't know science. The whole idea of science, especially physics, is reduce everything to its most common element. And if you reduce everything into its most common element, everything in the universe, as far as we know of, is made up of two things: fields and or matter. And matter being your various particles. In quantum mechanics, they're trying to reduce fields to particles. In relativity physics, they try and reduce particles to fields. Which of the two is more fundamental, we don't know. But as far as we know, on an everyday level, everything is made up of those two things.
There was like a chemical spill in this town. What I was trying to determine if those chemicals in the environment could cause things like hallucinations or could cause dizzy spells and things like that.
Well, whenever you're investigating something abnormal, anomalous, you want to look for chemical reasons, not just that they're affecting the people. Different chemicals affect us in different ways. You sniff glue or something, it's going to change your perception. You take drugs or something, it's going to change your perception. You physiologically react to different chemicals in different ways. Some physiologically, but some through your mind, your brain. They affect your senses. So it is, whenever there's any type of an anomalous phenomenon, citing a UFO, you might want to see if there's a chemical reason to it. Other than that, you would want to check the fields. It may be some type of electromagnetic effect. The chemicals deal directly with the brain, human brain. If you can't account for an anomalous phenomenon in the brain in that manner, it's not a hallucination, you know it's real, because it's seen, it's detected through sight, then you want to check the medium between the brain and the object, the anomalous phenomenon, and that would be your fields. You want to check fields and things like that and see if there are any alterations in a field that might cause a misperception by the detector, the human.
And can like a chemical spill where toxins are in the air, in the environment, can something like that change or alter, say, electromagnetic fields or magnetism in an area or the electromagnetic spectrum? Is there any possibility of that?
That seems highly unlikely to me. There might be some chemicals that might have magnetic effects, but I don't think they'd alter the environment physically in any way that could cause a change in electromagnetic spectrum. No, I I can't think of anything that would.
Is it more likely or probable that there is, say, life on a distant star or planet, or is it more likely that there is, say, existence on, say, a parallel plane or a parallel type existence?
It would be more likely that there's life on another planet within our four-dimensional space-time.
Can you do the same answer, but just say as opposed to?
As opposed to being on some other plane of existence, some other dimensionality than our normal four-dimensional space-time. But I can't discount the other. Science proves nothing with absolute certainty. We develop theories to describe things. We don't know, our theories are not absolute, they can always change. So we don't even like to use the word proof. A mathematician can prove something within the system of mathematics he develops based on his axioms. In our case, the axioms and postulates are decided by nature. So we can't prove anything absolutely exists. That's why we verify instead of proof. We can verify something to a very, very high probability, but that isn't considered an outright proof. Now, we assume that our laws of nature that we develop in physics, chemistry, and the other sciences are valid throughout all of nature, so they're valid throughout the whole universe. We know gravity, as far as we can tell, is valid throughout the universe because of our astronomical observations. We detect water molecules due to their vibrations in electric and magnetic fields. They give off electromagnetic waves at far reaches of the galaxy, so we can see water out there. So we know the elements that we know exist throughout the universe. So we assume the whole universe operates on exactly the same laws as we do. Given that, and given the fact that life evolved on this planet, we can assume that life has evolved in other planets throughout the universe. And one scientist, I can't remember his name, has an equation of how many different planets might have life. I don't think any scientist would say there is no life on other planets. There's an extremely high probability, very high probability, approaching a certainty that there is some type of life on other planets. What form that life takes, we don't know. The question, though, is not really, is there life on other planets? We want to verify that, yes. That's why we're going out there. That's why we're exploring the other planets to look for life. That's one of the primary reasons. But is there intelligent life? See, that's the rare thing, not life itself. We feel that's going to be everywhere. But intelligent life that has an intelligence like us. You look at the whole Earth. The Earth is 4.5 billion years old, and yet we've only had intelligent beings for 2,000 of those years. There are planets that are far older than our planet. There are planets that are far younger. Even if they evolve intelligent beings, would they be at the same level of intelligence as we are right now? That's the thing that's improbable. So we hope to find that. That's actually one of the scientific arguments against UFOs being from other planets. I cannot say that there are not other, I don't like to use the word planes of existence, because those terms are used by New Age people and like that. Let's say other dimensionalities. We live in a four-dimensional space-time continuum, according to relativity theory. We have 3 dimensions of space, 1 of time. Why 3 dimensions? We have no idea. We determine the 3-dimensionality of our space by the relative positions of material objects. So the matter that we see, chairs, tables, everything in this room, the matter that we see, we detect, determines the 3-dimensionality. The 3-dimensionality does not determine the matter. So therefore, there may be other dimensions. There's no reason why there aren't other dimensions. And if there are other dimensions, there's nothing in science that says there can't be other dimensions. If there are other dimensions, there may be other pockets of 4-dimensional space-time reality. That's your parallel universes, or one way from relativity theory of seeing your parallel universes. So there may be other pockets of the other universe in other dimensionalities, groups of 4, 5, 6, whatever dimensions within an infinite dimensional universe that have evolved life. Maybe they have the same physics laws we do. Maybe their speed of light is different, which would change everything. We don't know. But if they have some type of intelligent life, perhaps it could go between the different pockets of dimensionality. Speculation. Good fodder for science fiction movies, of course. Is it outlawed by science? Does science say it's impossible? No, science does not say it's impossible. All we can talk about is it highly probable? And we say it's not highly probable only because we don't have any evidence of it. Now, dimension is a funny thing. If there's a fourth dimension to our space, and I and other scientists believe there is, we're a minority, but we believe there's another dimension, things could pop in and pop out. Say if you take a two-dimensional surface and draw a circle on it, put a dot in the circle. You can't take the dot outside the circle because you can't cross over the line you drew around it. But say if that dot were a living being, it couldn't get outside the circle it's in. It'd be inside a closed room in the circle. But if you go to a higher dimension, it could actually go outside the circle without going through the circle to go to a higher dimension. So if you're talking about the reality of a fourth dimension to our space, we do not detect it because all of our detection devices, including our five senses, are based on material. And our material dimensionality is 3. Maybe there's another higher dimensionality in which our material portion doesn't exist. Then something could go, enter and leave this room without going through the walls, the doors to this room. That's just simple 4-dimensional geometry. So yeah, something could pop in and out of our dimensionality by going into and out of a higher dimension that's associated with our dimensionality. I think that's more what you're talking about. Actually, this whole idea of dimensionality was developed between 1870 and 1900. It's over 100 years old. It predates Einstein's relativity by 30 years. They're talking about this in the 1870s.
So it's actually more, I guess, plausible to consider the idea of a fourth dimension.
A fourth dimension, right. See, all of our senses and everything, since they evolved from our material world, matter is 3-dimensional, so we assume space is. But there's nothing that guarantees space is 3-dimensional. The only thing is all of our measurements are 3-dimensional because matter is 4-dimensional, or 3-dimensional, and we're using matter to do our measurements. So there's no reason why we couldn't have higher dimensions. No scientific reason. I'm still trying to imagine a 4-dimensional cube.
Yeah.
It's called a tesseract. Well, I contend that if you can imagine a 4-dimensional cube, it's called a tesseract. If you can actually visualize that, you'll become an enlightened being because you no longer see our 3-dimensional space in the same way. You'd see it in a whole new perspective, and that would be an enlightened perspective.
Well, is there anything else that you think I guess you can probably see a little bit where I'm going.
Yeah, you're looking at scientific possibility that may explain, within our present science, these phenomenon. You see exactly where you're going. And that is actually the correct scientific way to do things. There's sort of an unwritten rule in science. You can't invent an unknown to explain an unknown. And unfortunately, a lot of people without scientific backgrounds are always trying to invent unknowns to explain unknowns. An unknown being, say, a ghost. And so they invent some exotic type of matter to explain what a ghost is. It's made of phlegm or something, some matter that we don't know. Well, unless it can connect to our present science, unless we can put it in our present scientific terms, it's meaningless to us. You can always explain something by making up, you can always explain one lie by making up another, sort of. So that's a no-no in science. We have to explain things in the terms that we understand within our paradigm or our theoretical perspective. On the other hand, you have the scientists, a lot of scientists who are so conservative that they automatically say, if it doesn't fit our theoretical perspective, our paradigm, they say it doesn't exist. Well, they're as bad as the people who are inventing things, new things to explain things. As far as ghosts are concerned, I've been out on ghost hunts up in Parkersburg, and I've been with Susan Shepard and the Ghost Club and people from our parapsychology class, and we've taken pictures, and orbs appear on those pictures. And in one case, there's a picture of me looking at the back of my camera, and a picture is taken of me, and there's this cloud of something forming around me, just sort of back, front, and then up in front of me. And you can see it very clearly. Now, I know those pictures weren't faked, and I've shown them to some fairly well-known scientists who are actually parapsychologists. And they say immediately that those are the orbs or embers from the fire or something. And I explain, well, the fire was up over the hill 100 yards away through the woods. They couldn't be embers from the fire. And then I showed them orbs during daylight when there's no fire, no campfire. And some scientists refuse to believe or even consider the possibility. It's not believing. It's considering the possibility because it doesn't fit their theoretical perspective. They're as wrong as people who are making up things. Now, I've been in a haunted house, and what was thought to be a haunted house, a ghost had never been seen, but weird things happen in the house. Curtains rustle when there's no wind. Doors open and such. And we went to a closet, and I had an electric field meter. We went to a closet where seemed to be associated with some of this weird happenings. Again, no one's seen ghosts, just weird happenings, doors opening, clothes rustling, things like that. And everybody gets a really chilled effect when they go by this one closet. So I put my electric field meter in there. And the field meter goes, the needle is actually bouncing off the end of the scale, and it's going click, click, click like a Geiger counter from hitting the end of the scale. And I pull it out, nothing. I put it back in and going click, click, click. And the field meter is pegging off the scale. And one of my students says, well, that almost sounds like a Geiger counter. You know, it goes click, click, click. And no, it's just a needle pegging on the scale. Something was happening. It was an extremely strong electrostatic field. So I assume that when I stick my arm in, I've got a nice hairy arm, so my hair would stand up for the electrostatic charge. My hair wasn't standing up. So the field meter is telling me there's an electrostatic field there, a very strong electrostatic field, but the hair doesn't stand up on my arm. Really strange. There's something strange going on there. There was a field effect, but it was not a normal field effect. Now, I took my electrostatic meter home just to calibrate it. I put it up next to my TV, a 22-inch screen TV. The meter goes into the high zone, but it doesn't peg it. Yet I put my arm close to the TV screen and my hair stands up. So whatever that was, it was not a normal electrostatic field. For one, it had a vibration to it, the way it was pegging it. And it had to be extremely strong, much stronger than a big TV screen. Yet my hair wouldn't stand up. I don't know what was going on. It seemed to me to be some type of electromagnetic wave. But there was some field effect there. I couldn't determine what it was. There are weird things, yes.
We hope you enjoyed this episode of Eyes of the Mothman, the podcast. For more information about our program, or to find out where you can watch the original documentary film or purchase a limited edition signed DVD copy, please visit www.eyesofthemothman.com.